Okay, hello. In this class cast, we'll look at measurement and uncertainty. This is something that we always do in physics, so it's really important that we learn a couple of terms that characterize measurement. Okay, the idea here is that all measurements have a level of uncertainty attached to them. Okay, so we need to know the two terms, precision and accuracy, that describe uncertainty. So if you see a target here and there's three darts, you can see they're close together, so they're repeatable, and they're exact in some way. And so we call this precise. Okay, so the idea these measurements are repeatable, and they're somehow consistent. Consistent. Okay, so that's what we mean by precise. Accurate, on the other hand, is when they're close to a known value or a known target. Okay, so here they're all kind of together near the bullseye, so they're accurate. So it's how close to target value. Okay, so in this case here, the measurements are precise, so yes. Are they accurate? No, because they're away from the target. But in this case, they are precise and they are accurate. Okay, so how precise a measurement made depends on two things. First, obviously, the instrument we're using. So here you can see that there's one ruler that has these markings, and over here the markings are a little bit more finer. So with this ruler we can make the measurement of the nail as 4.4 centimeters, whereas maybe this ruler we can say, oh, that's 4.39 centimeters. Okay, so this would be more precise. Okay, but it also not only does it depend on the instrument, but it also depends on the skill. And this is, in this example, if you have a stopwatch, is reaction. Okay, reaction time. Okay, so if you have a more precise equipment, this does not necessarily mean that you're going to have something that's more precise. Okay, so it doesn't necessarily improve the uncertainty in your measurement. Okay, so a way to characterize or specify uncertainty and precision is through significant figures. Okay, they are essentially digits that carry meaning to the precision of a measurement. Okay, and there are some strict rules that go along with these significant figures. Okay, so the first one is all non-zero digits are significant. This is pretty straightforward. If you have a number like 145, this has 3 sig figs. Okay, every single digit here is significant. Okay, the second rule is zeros between other digits are significant. Okay, so if you have a number like 7005, this would have four sig figs. Oh my god, sig figs. Okay, so these zeros are in between digits, so they are all significant. Okay, the third rule is trailing zeros where a decimal is present. This is very important. So if you have something like 10.0, okay, the fact that there's a decimal and a zero after the decimal, okay, that zero is significant. So this would have 3 sig figs. Okay, this kind of number. Another example would be, same type of measurement, same value, 10.000. So you think it's, if you have $10.0 or $10.000, you have the same amount. But this implies way more precision because it's like to 3 decimal places. Okay, so this would have 5 sig figs. Okay, so way more precise measurement. Now, what's more important to understand when digits are not significant. This is a bit more difficult. For example, if I have a number like 0.012, okay, this only has 2 sig figs. Okay, the reason for that is all leading zeros are not significant, and this should make sense because something like 0.012, kilometers is the same measurement as 12 centimeters. So, it's the same number. So this definitely has 2 significant figures. So in that logic, so should this. Okay, so leading zeros, okay, are not significant. Okay, and the last one, it's an ambiguous case. It's probably one of the most confusing. Is if I have a number like 2,700. How many significant figures does this have? Well, it's kind of ambiguous because we don't know if these numbers here are significant. Okay, and so we say that if there's trailing zeros where there is no decimal place, okay, the zeros are not significant. Okay, so this would have 2 sig figs. Okay, so in order to make this a little bit more explicit, we need this thing called scientific notation. Okay, and so what we do is if we express the number as 2.70 times 10 to the 3, okay, this would say we have 3 sig figs, even though it's the same number. If I have 2.700, that 10 to the 3, this would have 4 sig figs. Okay, so this is what we call here scientific notation. Okay, and it's really important because it's useful for expressing ambiguous numbers, like numbers that have trailing zeros. It's also really useful to express large and very small numbers. So like, look at this number here, radius of hydrogen. So you don't want to be writing out 0.0000000, that's annoying, 0.53 meters. Okay, so we want to make this a little bit more concise. So we'll take that number and we'll put it to 5.3 times 10 to the negative, well, let's go. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we need to go to 10 times 10 to the negative 11 meters. Okay, so a couple of things about scientific notation is this first number is always between 1 and 9. So it's between 1 and 9. And it's always to the base or power of 10. And all the numbers that we specify here are significant. Okay, so this is 2 significant figures, this number is 4 significant figures, and this number here is 3 significant figures.